Welcome to the session Gain Better Insights by Training Machine Learning Models with SageMaker Debugger. My name is Natalie and I'm an applied scientist at AWS. First, let's look at why debugging and profiling is important. When we train machine learning models, then this is typically a difficult and compute-intensive task. When we create training scripts for our machine learning model training, then it may frequently happen that these training scripts contain bugs. These bugs may lead to a model training that is not converging because the model may suffer from overfitting, underfitting, vanishing gradients, or other issues. Trying to find the root cause of such problems is not always easy, and for sure it's very time-consuming. When we train machine learning models such as deep neural networks, then they are usually trained on large compute instances. State-of-the-art deep neural networks consist of millions of parameters, so we may have to train them on multi-GPU instances. Trying to use these instances as efficiently as possible is not always easy and requires lots of tuning. To train deep neural networks take a long time, and because of all that, we want to ensure that we use existing compute instances as efficiently as possible and find training bugs as early as possible so that we can use our given training budget as efficiently as possible. Let's take a closer look on debugging in the machine learning lifecycle. Machine learning is not just about creating and training models, but there are many different steps involved. One of the most important steps is data preparation. Only if we have high-quality training datasets will we be able to train a model that achieves high accuracies. During data preparation, we have to deal with feature engineering, deal with missing and corrupted data, and do data preprocessing. Debugging at this stage should help us to find dataset-related issues. For instance, if the data is not correctly preprocessed or normalized, then this may lead to a model that may not train well. Once we have high-quality training datasets, we are ready to train and create machine learning models. This is typically an iterative process where we try out different model configurations, different hyperparameters, and it may frequently happen that we end up with a training script where the model training does not converge. Debugging at this stage should help us to find these issues as early as possible, and we also want to be able to auto-terminate training jobs that would otherwise lead to suboptimal models. Debugging should also help us to get more insights into our model, for instance, trying to understand what are the kind of features the model is learning. Once we have a decent machine learning model, the next step in the pipeline is hyperparameter tuning. During that step, we try to find the best combination of hyperparameters that yields the best model accuracy. It may happen that we end up with a combination of hyperparameters that leads to a model training that does not converge. Again, we want to be able to automatically detect these issues and terminate training jobs ahead of time. Once we have a good machine learning model, we are ready to deploy the model. During deployment, what can happen is that the distribution of the inference data may be significantly different than the distribution of the data the model has been trained on. If this happens, then it may mean that the model does a lot of incorrect predictions. Debugging at this stage should help us to understand false model predictions. For instance, if you have deployed an image classification model, then you may want to use techniques such as saliency maps that show you what your model is paying attention to when it's doing predictions. That can help to understand better false model predictions. Now I would like to show you how you can use Amazon SageMaker Debugger to address the debugging challenges and in the machine learning lifecycle, as well as how to find issues related to resource underutilization. SageMaker Debugger is a feature that allows you to automatically capture tensors from your model training. We support what we call zero code change. That means, as a user, you do not have to modify anything in your training script, nor in your model. When you start your SageMaker training, you simply specify the kind of tensors you want to have emitted, tensors such as weights, gradients, and Debugger will take care of the rest. The data will be uploaded in real time to your Amazon S3 training bucket, and it will be stored there in a persistent way, which means you can either fetch the data while the training is still in progress or after the training has finished. We have added a new capability to SageMaker Debugger that supports real-time profiling. This feature is useful to find hardware resource underutilization. You can monitor system metrics such as utilization per CPU, GPU, network, memory, and I/O, as well as you can profile the kernels running on the GPU. Debugger comes with a set of built-in rules that you can use for automatic error detection. There are two types of built-in rules. One, to find model-related issues such as overfitting, vanishing gradient, underfitting, and many more. And the second type of rules you can use to find resource utilization issues. You can also specify actions and alerts with the rules. For instance, you can automatically stop the training or send an email and SMS notification. We also introduced a rule that creates a profiling report. This profiling report gives insights into the resource utilization issues and also recommendation of next steps. You can also use Debugger for real-time monitoring and real-time visualization. You can either use Debugger's library SMDebug to fetch the data on your notebook and inspect and visualize the tensors while the training is still in progress. You can also use SageMaker Studio to create interactive visualizations of the performance data. Let's take a look on the architecture. When you run training on Amazon SageMaker, then the training is running inside a training container. Debugger will now ensure that the tensors that you have specified will be automatically emitted to your Amazon S3 training bucket. If you run your training with built-in rules, then SageMaker will automatically spin up the rule containers that run on a separate instance. This means that the rule analysis does not interfere with the training. You can specify multiple built-in rules that run in parallel. The rules emit metrics to Amazon CloudWatch. So whenever a rule triggers, the metrics get emitted to Amazon CloudWatch, and you can specify CloudWatch alarms. You can then connect the CloudWatch alarm to a Lambda function to trigger certain other actions or to just create some custom workflows. The rules use the Amazon Simple Notification Service that you can use to specify notifications such as SMS and email whenever a rule identified an issue. You can also use the real-time monitoring capability while the training is still in progress. You can already start fetching the data and perform all sorts of visualization and analysis. Let's take a closer look on the real-time monitoring feature. SMDebug is the open source library of SageMaker Debugger. It's a library that allows you to access, query, and filter the tensors recorded by SageMaker Debugger. You can find the library on PyPI, so on your notebook instance, you can just do pip install SMDebug. If you run your training on Amazon SageMaker, then in the SageMaker Python SDK, you can now define a debugger hook config. In the debugger hook config, you basically tell debugger which kind of tensors to capture. It supports default collections such as gradients and weights, but you can also create your own custom collection. In this code snippet, I select now the gradients and my own custom collection for the Relo activation outputs. I simply have to specify a regular expression of the tensor names I want to have included. So I select here conf_Relo. Once the training is running, I can now use the SMDebug API to access and query the data. SMDebug provides a function createTrial that you have to point to the Amazon S3 path where the debugger data is located. Once you have the trial object, you can start iterating over the data. With trial steps, you get the different iterations that have been recorded by debugger. Per default, debugger will capture tensors every 500 steps. Trial.tensor is the function that you can use to access the actual tensor. You pass in the tensor name. In my case, I want to access the ReLU activation outputs of the first convolutional layer. With dot value and a specific step number, I'm accessing now the tensor at the recorded iteration. SMDebug will retrieve the tensor as a NumPy array, which means I can use tools such as Matplotlib, NumPy, SciPy to create visualizations and further analysis. So here I'm using the Matplotlib histogram function to visualize the activation outputs of my first convolutional layer across the training time. What we can see here in this visualization is that as my training is progressing, the distribution moves more and more towards zero, which means my model is actually suffering from the dying ReLU problem where more and more neurons are outputting zero values. And with just few lines of code, I can now easily create this kind of analysis. Now let's take a closer look on the demo. In the demo, I will show you 3 different use cases. First, we will look at how we can use debugger to collect tensors and select built-in rules to identify poor training jobs. In the second use case, I will show you how you can use debugger to collect performance-related data to identify how well was the training instance utilized. Last but not least, we will look at how we can now select actions to auto-terminate training whenever a rule identifies an issue. So let's take a look at the notebook. You can use debugger to capture any kind of tensors from your model training, such as the model inputs, the gradients, weights, activation outputs, loss values and accuracy metrics. And in the case of XGBoost, debugger can also measure the depth of the tree as well as feature importance. In order to run debugger with built-in rules enabled, you use now the SageMaker Python SDK and select the rule configs subpackage. The rule configs allows you to access any of the available built-in rules. As I mentioned in my introduction, debugger provides 2 types of rules. Rules to find model-related issues, such as vanishing gradient, loss not decreasing, overfitting, underfitting, class imbalance. And it provides profiler-related rules that you can use to identify performance-related issues, such as CPU and I/O bottlenecks, underutilization, workload balancing, and many more. You can now select any of these rules from the list here. In my demo, I select now the loss not decreasing rule. This rule will measure if the training loss is decreasing throughout the training, and if it does not decrease by a certain percentage, the rule triggers. Next, I select the class imbalance rule. This rule will take the labels into the loss function and determine how many class instances has the model seen throughout the training. Next, I select the date ReLU rule. The date ReLU rule will measure the number of dying ReLUs in the model. ReLU is the rectified linear unit. It's an activation function commonly used in many state-of-the-art deep neural networks, and it can suffer from the dying ReLU problem. The dying ReLU problem refers to the situation where a neuron will only output 0 values and then receive 0 gradients. If you have too many neurons in your model that suffer from that problem, then it cannot effectively learn. For each rule, you can also specify rule parameters that allow you to tweak the rule for your specific use case. Now I specify the debug hook configuration. And as I mentioned in my presentation, debugger supports default collections such as weights, bias, gradients, but you can also create your own custom collection. And the debugger hook configuration will basically tell debugger which kind of tensors to emit. And this is useful if there are tensors that are not already collected through the rule configuration, which tensors that you want to monitor to be able to perform, for instance, some real-time visualizations. Now I'm ready to start a SageMaker training. I'm going to train a PyTorch model. So I use the SageMaker PyTorch Estimator API. My training is defined in the train.py file. I want to run the training on a P2 instance. And in order to enable debugger, I just have to pass in the debugger hook config as well as the list of rules. Now I start the training. I just call estimator fit. Behind the scenes, SageMaker will now spin up the training container, and debugger will ensure that the tensors that I have specified in the debugger hook config will automatically be emitted to Amazon S3. SageMaker will also automatically spin up the rule containers for the class imbalance, the date relu, and the loss not decreasing rule. Those rules will run in a separate container on a separate instance, so the rule execution does not interfere with the training. They fetch the data from Amazon S3 and perform the analysis. As a user, I can now check the rule status from the Python SDK by accessing rule job summary, or I can go to the experiment view. So when you open experiment and then select your training job, you will get this experiment view here, where there's a debugger tab that shows you which kind of rule have been running and which issues were found. In my case, the class imbalance and the loss not decreasing rule triggered. So now let's go to the next use case where we look at the performance data. We will use debugger to capture system metrics and identify resource underutilization. Debugger can capture metrics such as the utilization per CPU core, GPU, I/O, network and memory. And it's also capturing information from the training itself, such as the time spent in data loading, data preprocessing. You can enable Python profiling for the training script. As well, debugger can measure the operators that have been running on GPU. When we look at the machine learning pipeline, then the first step is to read the input data that is either available on a local or remote storage component and read it onto the local CPU RAM. The CPU will typically do the data preprocessing, prepare the data batches that are then sent to the GPU. The GPU will perform the training, and a very common performance issue is CPU bottleneck. This means the GPU is waiting for data to arrive from the CPU, so the utilization drops, but at the same time the utilization on the CPU is very high because it's busy preprocessing the data. To collect the performance metrics, we define now a profiler config. In the profiler config, we tell debugger to select system metrics at 500 millisecond sampling interval. We also specify a framework profile. The framework metrics refer to the metrics captured from within the training script. And here we collect it for 2 steps. What debugger will do is it will take those metrics from the different data sources and correlate them. So for instance, it can now take the system metrics, like here the GPU utilization, and we can see that there are certain timestamps when the utilization drops to 0. So debugger can now identify what has been happening at the same time in the training script to identify potential performance root causes. In this example, we see that the drop in utilization correlates with data preprocessing. So the root cause could be an issue in the data pipeline. We can now use the profiling report as well as the visualizations in Studio to get some more insights. So in order to open the Studio visualizations, you go in the experiment view on your training job and then select Open Debugger for Insights. Let's take a look. The Studio visualizations provide first a high-level overview of how long did your training run, when did it start, how long did it run, how much time was spent in the training loop, initialization and finalization. The initialization is the time from when the training job started to when the first forward pass was performed in the model. And typically you want the initialization time to be minimal, because the actual training, when the GPU will be used, is mainly during the training loop. So you want the training loop to be the phase where you spend most time in. The overview panel also provides an overview of the system resource utilization. This is aggregated per worker node, and we see that the total GPU utilization never exceeded 75%, and the median utilization was always around 63%. So obviously the GPU was underutilized. We also see that the CPU utilization was not very high. The median utilization was only about 24–25% and never exceeded 80%. The overview panel also provides some information about the resource-intensive operations, listed by and sorted by the time. And you will also see the executed rules and which of them triggered the most. In my case, this was the step outlier rule. We can now go to the node overview to get some more insights into the performance data. Here we see the time series charts for CPU utilization as well as GPU utilization across the training job time. We see that the CPU utilization never really exceeded 24%, and in the case of the GPU we can see that it's highly fluctuating. So obviously our training suffers from some performance issues. We can now download the profiling report. We can also access the profiling report directly via Amazon S3. The profiling report gives us some further insights. In the beginning, it provides a similar high-level overview like SageMaker Studio, like operators on CPU and GPU, the resource summary statistics, and for each rules, it will provide some further insights. So for instance, we have seen a step outlier rule triggered. The profiling report indicates that the average step duration was 0.02 seconds. It then also provides a histogram of the step durations. And the rule triggered because there were certain step durations that took significantly longer. Debugger will then take those timestamps and correlate it with what has been happening inside the training script at the same time to find potential root causes. The profiling report also gives some more insights into the GPU utilization. It provides box plots as well as workload histograms. The workload histogram shows us the GPU utilization on the x-axis, so from 0 to 100%, and then it counts how often has the GPU been utilized at 0%, 50, 60, 80, 100%. And this kind of visualization is especially useful if you have multi-GPU training, and you can then more easily identify how well was the workload balanced between multiple GPUs. What we basically see here is that the utilization never went beyond 75%. The profiling report also includes some more details about the data loading part. So for instance, on my training instance, I had 8 CPU cores available, but I was only running 1 data loader. So this could have been optimized. Furthermore, the rule found that I did not use pin memory, which is a feature that can greatly impact the performance because it enables faster data transfer between CPU and GPU. The profiling report also provides a histogram of the data loading times. So we see that there are a lot of outliers, so it's not like a uniform distribution. So it may indicate that there is some data loading issue. The profiling report also gives some insights into the batch size, whether this could have been increased or not. So in my case, it's recommending me to potentially increase the batch size, and a debugger will measure the GPU memory, the GPU utilization, as well as the total CPU utilization to determine whether the batch size could be increased. So for instance, I see here that the GPU memory is not really fully utilized. It's basically less than 12%. At the same time, the GPU utilization is small, which means my training was not GPU bound. So by increasing the batch size, I would not only increase the memory footprint on the GPU, but also the utilization, because more data will be processed in parallel. The profiling report will also give some more insights into whether the training suffered from CPU and I/O bottlenecks, which was, however, not the case in my training. So now we have learned how to use Debugger to find model-related as well as performance-related issues. Now let's go to the third use case. Now I would like to show you how you can use Debugger to enable actions. For instance, we have seen that a loss not decreasing rule triggered. So now I use the action list and I can select either stop training, email or SMS. And for each rule I can specify its own action. So in the case of loss not decreasing, I want to stop the training when the rule triggers, because trying to train a model where the training does not converge anymore would be wasted compute time. And with Debugger I can automate this action by just specifying this action list. And in my case, when I run now the training with auto termination, I can basically see on the loss curves that my training was terminated around 1500 steps. So I only run the training in half the time compared to the training where I ran without auto termination. So in this demo you have learned how to use Debugger to find training issues early on and how to auto terminate the training. And we have seen how we can use Debugger to get real-time insights. I highly recommend you to check out our recent publication. In this paper, we describe in detail the architecture of Amazon SageMaker Debugger, as well as all the available built-in rules, the kind of issues they can detect, and also we describe how you can possibly fix your training script to mitigate some of these issues. We also describe several use cases of how you can use SageMaker Debugger in end-to-end analysis workflows. If you would like to learn more about machine learning on AWS, then please check out our online courses. Thanks a lot for attending this session.